Hi everyone, and welcome to Eric's Electronics Workbench. In this video, I'll be explaining how to set up an isolated dim bulb tester. I'll answer some of the common questions that go along with setting up a tester like this, what its purpose is, and how each of the components in the tester functions. So let's get started. Here we are looking at the three main components of an isolated dim bulb tester. So on the right-hand side we have the isolation transformer, which provides electrical isolation on the AC line. In the middle is the incandescent bulb, which offers the current limiting. And on the left-hand side we have the Variac, which is a type of auto transformer, and that allows us to vary the AC voltage going to the device that we're powering. So you may be asking yourself, what is an isolated dim bulb tester exactly used for? How do you use it? Well, when you're testing vintage vacuum tube type equipment, so vintage radios, audio amplifiers, and even vacuum tube based test gear, if it's the first time the equipment has been powered up, you often want to power up the equipment very slowly, and you can do so by varying this voltage very slowly as the equipment is powered up. That can help to form capacitors. Now, in many types of vintage equipment, the capacitors need to be replaced. That gets into a different topic, but if it's the first time you're powering it up and you're trying to test the equipment, again, powering it up very slowly by bringing the voltage up, very, very slowly is a very safe and good way to power up the equipment. You don't want to just take the device and plug it directly in the wall outlet and see what happens. That could certainly damage it, particularly if it hasn't been used in a long, long time. The current limiting provided by the incandescent bulb, and that's where the name dim bulb comes into play, is important because if there's a short in the device that you're powering, this bulb will get very bright. So the wattage of the bulb is very important. This is a 100-watt bulb. I find that 150 or 200-watt bulbs tend to work very well, but it depends on the device that you're powering up and how much current it needs to operate. Voltage will drop across the bulb, and if you have, let's say, a 25-watt bulb in here, a lot of voltage will drop on the bulb, and the device that you're trying to power up may never really power up enough for the tubes to come into emission, and it'll just really sit there and not do a whole lot. So sometimes a little trial and error to see which bulb is needed, is necessary. I have seen dim bulb testers that have several bulbs connected and some switches for selecting different bulbs. In my tester, which I'll show a little bit here, I just use one bulb and I change it out as necessary. Now, in my tester, and a feature that I would recommend is to have a switch across the bulb that takes it out of the circuit by shorting the bulb out, because when you're testing a piece of equipment and you want to bring it up to full line voltage and you know that it is in good working order, you no longer need the current limiting offered by the bulb, and you want to take the bulb out of circuit. So if you have a switch that just shorts across the bulb is out of the circuit. That also allows you to use this arrangement on testing modern pieces of equipment that you want electrical isolation, you want to set the line voltage precisely, but you don't need the current limiting. So again, a switch that jumps across the bulb is a very good idea. And again, I'll show my setup that I have, and I do have a toggle switch that is across the bulb that allows you to select the current limiting or not. So again, the dim bulb tester is a very safe way to power up a vacuum tube equipment, and it is also very useful for powering just general pieces of equipment that you're working on where you want the electrical isolation for safety. The isolation for safety is so important on vacuum tube equipment because many types of vacuum tube radios have one line of the AC cord connected to the internal metal chassis. So they have non-polarized plugs in most cases, and if that plug is turned one way versus the other way, it's a 50-50 chance that you have the hot AC line connected to the chassis. So you'll get a nasty, if not lethal, shock if you were to come in contact with that chassis, when testing the equipment. So an isolation transformer provides electrical isolation from the AC line in the shop or the facility that you're at, and the secondary side, which is powering the device that you're testing. This secondary has no reference to ground, so it greatly reduces the chance of electrical shock if you were to come in contact with a live or hot chassis that had that line connected, from the cord directly to the chassis. The isolation transformer is absolutely critical when testing that type of equipment. But again, it's a good idea when testing any type of equipment that you're working around the AC line, so that isolation is very useful. And on my own bench, I use the isolation transformer tremendously, almost exclusively when I'm working inside a piece of equipment to have that protection from the AC line. Now, of course, shock hazards still exist within a piece of equipment, within its power supplies, but again, the AC line is what you're protecting against the shock hazard. And when you have a hot AC chassis, which can happen in vintage equipment, the isolation transformer is absolutely critical. Now, this transformer is a 1-to-1 turns ratio, so the voltage on the primary is the same as the voltage on the secondary. It's important to note that a Variac has no electrical isolation, all right? That's why this is required in addition to this Variac, which again has no electrical isolation. It's basically one continuous winding in here, and then the knob that you turn is moving a variable tap on that winding, all right? So it's a type of auto transformer that basically the tap is adjustable. Now, an isolated dim bulb tester typically would be mounted in a rather permanent fashion. Typically, you're not going to have these components across the workbench. You're going to want to have these permanently mounted. And again, I'll show my setup. It is a permanent installation. Certainly, a transformer like this that has exposed terminals needs to be in a protective housing, an insulated type housing, because you can't have terminals like this that are exposed. Any wiring needs to be properly insulated, and many Variacs are available like this, where they're sort of an all-in-one. This has a cord on the Variac, so it can be plugged in, and you have an outlet, a switch, and an amp meter. So this is an all-in-one solution for a Variac, but again, it provides no electrical isolation. If you use a Variac like this, you may need to modify the cord or wire it in permanently. Variacs are also available that are not in a housing. They could be panel mounted or mounted in a separate type chassis. So again, that's a personal preference on how you want to make the final installation. But again, these are the main components that would be required in an isolated dim bulb tester. Now, the term dim bulb comes into play because this bulb, in normal use, when it's in the circuit, will be glowing just very dim. You'll just have a slight glow across the bulb as a little bit of current is flowing through it, and that's what you typically want to see. If the bulb glows very, very bright, then you know that there is an excessive current draw, possibly even a short circuit on the device that you're testing. Or the bulb that you've selected is too low of a wattage. So if you start with a 25 watt bulb, it's going to glow very, very bright in most applications. If you put a 200 watt bulb in and it starts to glow very bright, that's a good indication that you may have excessive current draw. Many types of vintage radios and amplifiers and even test gear won't make a 200 or 250 watt bulb glow extremely bright. That just is that would be very unusual. So as you use a dim bulb tester, you get a feel for how bright the bulb should glow. And again, if it's glowing very bright and it's maybe a 60 watt bulb, you might want to increase that to 100 or 150 watt. But you need to choose a bulb that's appropriate for the device that you're testing. So we have three components that create the dim bulb tester. A common area of confusion and a common question that comes up is, what order do these components get installed? I mean, do you use the incandescent lamp before the isolation transformer? Does it electrically go between the transformer and the Variac, or is the Variac first? Does it matter? Well, let's take a closer look at the different configurations and how these three components can be connected, and let's see exactly what effect it has, if any, when they're connected in different configurations. And hopefully that will help you if you are designing and building your own isolated dim bulb tester. Now, before I get to that part, I'll show you the isolated dim bulb tester that I actually have on the bench, and I want to call out something that's very, very important about what's sold as an isolation transformer and in fact is not an isolation transformer, and it has to be modified if you're going to use it. A transformer like this is definitely an isolation transformer. It's very clear. You have a primary, you have a secondary. These jumpers on here are just selecting the taps. This can actually change the voltage depending on which taps you use, so it could step up or step down. I have it set for a 1-to-1 ratio, so the input voltage is the same as the output voltage. But there are isolation transformers that you can purchase that are not actually isolation transformers, so I'll show you that next. Here we are over on the corner of the workbench looking at the isolation transformer that I use on my isolated dim bulb tester. So you can see it's made by Tripp Lite, and it says isolator. It has a nice illuminated rocker switch for the main power on and off. It has a steel enclosure. It's based on a toroidal type transformer design. And on the back panel, it has the AC outlets that are connected to the secondary of that toroidal transformer. So the reason that I wanted to mention this isolation transformer is because if you pick up one of these Tripp Lite isolators, they are not in fact an isolation transformer as produced by the manufacturer, and here's why. So here's a schematic of what is actually inside the unit as the manufacturer assembles them. As you can see over here, we have the primary, we have the hot and the neutral and chassis ground. You can see there's the 1-to-1 isolation transformer. But down here, there's a link on the neutral, all right? So this is the secondary going to the outlets on the back of the unit, so you have the hot, the neutral, and ground. But the neutral here and the neutral over here, so primary to secondary, has a link between them. So this is not an actual isolation transformer. And this link needs to be removed so that there is complete electrical isolation on this side and no connection to the primary. Now, the manufacturer puts this link in here to tie the neutrals together really for a safety reason, because this is intended to be used with consumer electronics, stereo equipment, amplifiers, things like that. It's really intended as produced by the manufacturer as a way to eliminate noise, issues like that with the AC line, and they wanted the neutrals connected together. But when you're testing the vacuum tube equipment that I previously mentioned, you want complete electrical isolation. And the reason that this does not work is because this neutral being connected back to the neutral that goes ultimately to your breaker panel, the neutral is connected to earth ground in your breaker panel. So you effectively have the neutral over here on the secondary going to the piece of equipment that you're working on, going to earth ground. Well, you're standing on earth ground when you're working, and so now a shock hazard exists between the hot. If your hand comes in contact with this hot, it goes through you, through your feet, through something that you're standing on, through earth ground to the breaker panel, and then comes back over here to the other side of the transformer. So that won't work. You need complete electrical isolation from one side to the other. And this link again needs to be removed so that the hot and neutral over here have no reference to anything, in the outside world, so to speak. You don't want any reference to a ground connection. All right? So if you pick up one of these isolation transformers, a Tripp Lite, there may be others out in the market as well, but it's always a good idea to look at the design internally and see if there's any connection like that between primary and secondary. You can do a quick test with an ohm meter and basically verify that. If you take an ohm meter and connect from any of the connections on the AC input on the primary, you should have no continuity whatsoever to the secondary. Continuing on with the isolated dim bulb tester that I use on my workbench, you can see the Variac that I've incorporated into that setup is made by General Radio. And the Variac itself is this knob, and you can see as the voltage is increased, we get a reading on the AC voltmeter. Goes to 120, and then you can see we can turn it past that and get some voltage boost as well. So that gives us a complete range of AC voltage to the device that we're testing. We have a watt meter, and there's also the AC amperage. The amp meter range can be 1 amp or 5 amps, and the watt meter 150 or 750 watt full scale. All right. These various fuses are in the circuits as selected by the amp meter range or the watt meter range, and then of course the main power switch. Here we are looking at the final part of the dim bulb tester arrangement that I have on my workbench. So you can see here we have a switch box with a toggle switch installed and a socket on top that's permanently fixed to the top of the box. I have a 150 watt incandescent lamp that's in place right now. This can be changed to other wattages depending on the device I'm testing. It's also important to note that this cannot be an LED or fluorescent lamp. It must be an incandescent bulb. And then over there we have the AC outlets where the device that I'm testing is plugged into. So right now I have a bulb that's just simulating a load, because if this bulb is not installed, then there was no current flow and this bulb over here would not light up. So you can see if I remove this bulb like so, that lamp shuts off. All right, now if I turn this like so, this is now shorting out this lamp, so it turns off, and the full voltage is applied to the sockets. The voltage that's now being applied over here is whatever the Variac is set to, which right now it's 120 volts. All right. So if I put the current limiting back in place, some voltage drops across this bulb. The load voltage drops down some. Now, right here I have a cord. You can see the ends are just the ring terminals on the end of this cord. Right here, all right, that cord, you can see it's just going over to the second outlet below the one that the bulb is installed. Let's say the device that we're testing develops a short circuit, all right? Well, if these touch together, that creates a direct short across that outlet down there. No problems. All that does is makes this bulb turn on to full brilliance, all right, because all the voltage drops across this bulb. So if you're testing a radio or an amplifier or something like that, and something bad happens inside and it shorts out, you can see those ring terminals right there. There's just a focus on it there, but you can see a little bit of a spark between those ring terminals right there. But certainly nothing like the current that would flow if there was no current limiting at all and you had a direct short. You would have a lot more current would flow, at least until a fuse blew or there was, you know, something else was damaged. But in this case, the current is limited by the maximum current that can flow through the bulb that you've installed over here. So if you wanted a lot of current limiting, use say a 25 watt bulb, a 60 watt bulb, something like that. This is 150 watts. You could use 200 watt. I have a 300 watt bulb that I can install in here for something that's, you know, larger and requires more current just to operate normally. But again, even with a 300 watt bulb, if there's a direct short, you would have nowhere near the current flow that you would if you had no limiting whatsoever through the bulb. So a question that often comes up with dim bulb testers is, what's the correct order to place the isolation transformer, the incandescent bulb, and the Variac? Or does it even matter? Well, we'll take a look at all of that, and I'll also explain the order that I have my system arranged in and why I chose the order that I did. So I'll get the camera repositioned and we'll continue on. A common question that comes up when you're designing an isolated dim bulb tester is, what order should the components be placed in? So should the incandescent bulb be electrically first, or should it be between the Variac and the isolation transformer, or what if it's placed on the secondary side of the isolation transformer? So we're going to find that out. I have 4 different circuits that we'll work through, 4 different configurations of these components, and we'll see exactly what effect it has when they're connected in different variations or different configurations. Now, I have a schematic drawn for each configuration. I'll show you that in a moment. And on the schematic, I have it marked as DUT, or device under test. Normally that would be the radio or a piece of test equipment or an audio amplifier, something like that that you're working on. In our test circuit here, the device under test is replaced by this Fluke 117 digital multimeter. It's set to AC current or AC amps, and it's connected across the secondary, in this example, of the transformer, the isolation transformer. This meter is acting like a direct short because in the AC current or amps position, there's an internal shunt between these two test leads internally here, so there's a very low resistance. So this is acting like a short circuit across the transformer right now, and it will indicate the current that is able to flow through the secondary windings that would be limited by the incandescent lamp, because that's the whole purpose of this circuit and this setup, is to have current limited to a very safe value should a short circuit occur. Normally when you're using it, there would not be a short circuit, over here. You would just be powering the device that you're trying to test. But if something goes wrong and it does short out, we want to know what would that current be limited to. Now, I've already mentioned that the wattage of the bulb does change that current limiting. So in all of these tests, this bulb will remain the same, and it's a 100-watt bulb. And that's a value that you might find is suitable for many types of radios and things like that. But this could be increased to, say, 300 watts, or maybe something as small as 25 or 60 watts. Now, if you're following along, you do so at your own risk. I strongly suggest you do not reproduce these test examples that I'm going to go through because of the danger involved. There's exposed line voltage on the various test leads that you can see here. The test leads have to be clipped to the plug on the end of the cord. So really a dangerous setup, and again, I strongly suggest that you do not reproduce this setup. If you're building an isolated dim bulb tester, of course you do so at your own risk, and it needs to be done in a very safe way, and it would of course be wired in a very permanent configuration with everything being insulated and protected, so that you can't come in contact with it in any way. So when these tests are running, in no way would my hand be coming anywhere near the various points on these test leads, using common sense and being very, very cautious, because again, we have line voltage coming in here. All right, so for the first test, here's the schematic, and you can see that in this configuration, we have the hot AC line coming in, all right, to the incandescent bulb. That's that 100-watt bulb. It's going to go through the Variac, and the Variac taps off on the winding with this movable tap. Okay, so that's this knob right here. And the output from the Variac comes over to the isolation transformer, and the isolation transformer then returns back on the neutral. So on the secondary side of the isolation transformer, over there, we have the device under test, DUT, which is the Fluke 117 digital multimeter, and it's in the current position, so it's acting like a direct short across these windings right here. So we're going to find out what is the current that can flow through these windings when we put full 120 volt AC on the input over here. All right. And again, if you're following along, you do so at your own risk. So just be cautious and take care. All right, so I'll increase the voltage. And we can see the bulb comes up to full brilliance. And there's 120 volts input, and we can see we have 0.833 amps flowing over there. All right, so that's our current limiting. But something happens in this configuration. I'm going to zoom the camera in because you may not have noticed. Yeah, that works a little bit better. You can see in there, pardon the camera movement. So you can see the 5 on the scale right there, so that's 5 amps, okay, right up in there. And then the next tick mark over here is 10. There's a 10, I think you can see that right, it's a little hard to see in the scale, but right over in there, that's 10 amps, all right? So that gives the indication of the current that's flowing through the Variac. Now, we have the incandescent lamp that is electrically first in the circuit, but incandescent lamps have a very low resistance when they're cold, and that resistance rises up as they get warmer. Well, the bulb is off when the Variac is turned down to 0. So right now there's no current flowing. The bulb is acting as almost a direct connection, very, very low resistance. So as I increase the Variac to the initial settings, watch that meter for the current flow. You can see it jumps up very high. And then it begins to fall, all right? So right there is 120 volts on the Variac. The incandescent lamp is at full brilliance. And again, there's 0.823 amps flowing on that secondary of the isolation transformer. You would also have roughly the same current flowing over here. So the meter is not hardly indicating at all. It's because it's a very low current. But you can see it jumps up very high right there at the beginning. And you can almost hear a little bit of arcing in the Variac because of the higher current flow. So what does that mean? Well, this configuration is not the best choice because having the bulb first causes a problem of high current flow at low voltage settings of the Variac. That can pose a problem, with just excessive wear on the contacts of the Variac, and it's just not the best arrangement. Other configurations, as we'll go through, don't have that problem, and I'll demonstrate that shortly. So keep that in mind, that the configuration of putting the incandescent lamp first has the negative effect of high current flow at low settings of the Variac, particularly when you have, or really only when you have, a very heavy current on the secondary, or a direct short for that matter on the secondary of the isolation transformer. If I remove the short, which I will do now. Take that off. Okay, so the secondary of the transformer has no connection to it. All right, so there's no load connected right now. And if I increase this up, okay, you can see now, back the camera out, you can see over here, this is at 120 volts. We have no current flow, so the lamp remained off. This never jumped up. All right, and if I bring this back down again, you can see that jumpy high current that we were getting initially is not there when there's no load. So if you had no load or very light load, you wouldn't have that effect. But a heavy load or a short circuit on the output causes a lot of fluctuation and a lot of heavy current to flow initially. All right. So we'll move on to the second configuration, and I'll reposition everything and get that set up, and I'll be back. Here we are looking at the second configuration of the three components. So in this configuration, we have the AC line voltage coming into the Variac first. The output of the Variac flows through the incandescent bulb, and then from the bulb it goes into the primary of the isolation transformer. So on the secondary of the isolation transformer, you can see I have the Fluke 117 digital multimeter connected, AC amps or current position, and it's connected across the secondary, so this is acting like a short circuit on the secondary. So here's the schematic of that setup. You can see the DUT, device under test. That is the digital multimeter. And you can see over here the Variac, the AC hot and neutral line coming in. The movable tap within the Variac right here selects the winding that we want for the voltage. The further up this is, the more voltage you have. As this tap is brought down closer this direction, the less voltage comes out of the Variac. All right, so it comes through the incandescent bulb, through the primary of the isolation transformer, comes back around to the neutral. So everything is turned on and ready to go. We'll increase the voltage. You can see the incandescent lamp starts to glow. We have current flow over there on the amp meter. And I bring that up to about 120 volts right there. We can see we have 0.858 looks like. Yep, 0.857. So very similar current limiting to the other configuration. Tops out, about the same amount of current. But notice over here, when you increase the Variac, we don't have that spike of high current initially. The short circuit remains, but this initial movement of the Variac over here where the voltage is very low, you can see the bulb just begins to glow a little bit, but there's no jumping up with the excessive current like the first configuration. So this configuration works very well and would certainly do what we need from an isolated dim bulb tester. Now there is one slight issue with this configuration, and it becomes apparent if you have a smaller wattage bulb. Again, this is a 100 watt, so I'll change this to a 25 watt bulb and I'll show you what that effect is. I now have a 25 watt bulb installed. Everything else remains the same, but I've disconnected the amp meter off of the secondary over there, so you can see the test lead is laying right there on the bench. So the negative test lead is still clipped on, but the positive lead is sitting down there. So this is taken out of the circuit. There is no load on the secondary of that isolation transformer. So with a smaller wattage bulb right here, this will glow with less current flow through it than the 100 watt bulb. So if I increase the Variac, again, we have no current flow, so there's nothing going on over here, but we can see that this bulb is beginning to glow. So this is set to 120, so this is applying 120 volts to the primary of the isolation transformer, but we have some current flow and the bulb glows. And again, there's no current flow on the secondary. So with this configuration, slight, if you want to say a negative effect or maybe a slight disadvantage of having the bulb in the middle is that this bulb, particularly with smaller wattage values, will glow all the time. And the reason is there's always some current that flows through the primary of the isolation transformer. Transformers aren't a perfect component, and there's losses due to heating, and there's always some current that flows in a transformer winding even with no load on the secondary. So that's very obvious with this bulb glowing right now, and there's absolutely no load on the secondary. So this is dropping some voltage, okay? There's some voltage across this bulb that's being lost, which means that the output of this transformer will not match the output of the Variac, all right? So if this is putting 120 volts out right now, we can see over here it'll be less, and I can actually demonstrate that with a voltmeter. All right, I have the voltmeter in position, so we'll take a look at what the voltage is on the output of the Variac, and we'll take a look at what the voltage is on the output of the isolation transformer. Disregard the fluctuating numbers, that's just because the leads are floating. If those are brought together, it falls to the millivolts. All right, so if we take a look here, you can see there's 120.8 volts coming out of the Variac, all right? And I will go to the other side of the camera here, and you can see there we have substantially less, 72 volts. All right, 72 volts. So that voltage is lower because the voltage being dropped across that incandescent lamp. Now, if you use a higher wattage incandescent lamp, and I'll go back to the 100 watt bulb, you'll see that the voltage is less, but it still will probably be down some over there compared to what we have coming out of the Variac, because there'll be a slight loss across that bulb. All right, so I'll be back in just a moment when I get the bulb changed out. Okay, I now have the 100 watt bulb reinstalled. So we'll go back to the Variac. You can see 121.4. That's the voltage coming out of the Variac. And again, I'll go around to the other side of the camera here and take a look at the output. You can see 118. All right. So definitely a higher voltage with the higher wattage bulb. Again, no load on the secondary over here, but there is some loss across that bulb. You can see 118.4, and we have 120, 121 going into the isolation transformer. So a slight trade-off with this setup is that you will lose a little bit across this bulb. You can see it doesn't glow with the 100 watt bulb. There's not enough current flow to cause that to happen, but you're still losing a little bit of voltage across that bulb. All right, I'll go to the third configuration and we'll take a look at that arrangement. I'll be back in just a minute. Here we are looking at the third configuration for the isolated dim bulb tester. So in this configuration, we have the Variac first, the isolation transformer is second, and then the incandescent bulb is connected on the secondary of the isolation transformer. So the device under test, in this case we have our amp meter, is connected from the other side of the incandescent bulb, and it comes through the amp meter and then back to the secondary winding. So electrically, here's the schematic for what we see in front of us. So we have the AC line, hot and neutral, coming in through the Variac. The tap on the Variac comes over here, applies voltage to the primary of the isolation transformer, returns back to neutral. On the secondary windings on the isolation transformer, it would come through the incandescent bulb, through the device under test, and then back to the other side of the winding on the secondary side. All right. So the AC line voltage is being applied right now to the Variac. I'll bring the Variac up. You can see the bulb begins to glow. We do have current flow. Bring this all the way up to 120 volts right there. We can see 0.857 on the amp meter. So with a direct short being applied through the, basically on the other side of the incandescent lamp, because again this is now not across the secondary windings. One side of this amp meter is connected to the incandescent bulb. All right, move that bulb over to the other side of the transformer for this setup, and you can see the current flow through the meter, 0.856, but again this meter would be simulating the device that we would be testing. So if the device failed and had a direct short, we'd be limited to 0.856 amps with a 100-watt bulb. A larger bulb, you would allow more current to flow. A smaller bulb, you'd have less current to flow. So this arrangement works very well. There's no really issues with it. It functions very, very well. You can see as I bring this down to those low voltage settings, it does so very smoothly. There's no spikes in the current flow like we saw in the first arrangement. So really there's nothing wrong with this setup. It does work well, but there is one slight disadvantage to this setup, and that is if you have a Variac that has built-in metering, this meter is showing the total current flow of everything in the circuit, and it's going to show the current flow that is lost as heat in the transformer. So any indication on here is going to be the current that's flowing through the device you're testing, but in addition any current flow that's lost as heat in the transformer. So that's typically not a lot. It is a small amount, but if you have a very sensitive amp meter that's in your Variac, the general radio Variac that I previously showed in my setup is quite sensitive in the 1 amp setting, and it would show the current flow that is going through the transformer that's just being lost. It's just the current that flows under no load. You would see some indication, again very similar to the current that we saw flowing through the 25-watt bulb when it was placed between the Variac and the isolation transformer. Well, in this case, this meter would be showing that current flow. All right. So if you want a Variac that has built-in metering to show only the current that your device under test is actually drawing, and you want to disregard any losses in the isolation transformer, then we need to rearrange these components. And that brings me to the fourth setup, which is the setup that I have on my bench. So the components that I previously showed you, my isolation transformer, the general radio Variac, and the bulb that I have connected, the arrangement that I'm using is going to be identical to this fourth configuration. So I'll reposition the components and I'll be back. Here's the fourth and final configuration of the components for the isolated dim bulb tester. So this is the same layout electrically that I use on the tester that I have on my Workbench, and it works as follows. So you can see on the schematic we have the AC line, the hot and neutral. It's applied directly to the primary of the isolation transformer. The secondary of the isolation transformer is applied to the Variac, and the Variac, that movable tap within the Variac, is right here. It comes out, it comes over to the incandescent bulb. The other side of that incandescent bulb goes to the device under test, and from the device under test it's returned back to the Variac. This is a common point. You can see the isolation transformer secondary and the other side here, the Variac, are brought to this common point, as well as the device under test. All right. Now I did draw the switch right here. This is a switch that I previously showed on my setup where I can bypass that incandescent bulb, all right, that little switch box with the bulb on top of it. So when you close this switch, it shorts out the bulb and you have no current limiting. So it's very, very important to remember that when that switch is closed, in no way do you have any current limiting in this setup. But that's useful for being able to apply full line voltage to the device that you're testing. And again, you're isolated, but you're able to have that full voltage applied to it. So there are many times when I do have that switch closed because I'm testing something that I don't want current limiting, but I do want isolation on, all right? Now in this setup here, there's no switch across the bulb, but I included it on the schematic just for clarity so that you could see how it would be electrically included if you're building one of these yourself. So the system is powered up. We have AC line voltage on the primary of the transformer over here. You can see the little indicator is on down there. So I'll go ahead and increase the Variac. You can see the current rises up very smoothly. The bulb is very bright because, again, we have a short on the output here through that bulb, and it's limiting the current. The short is, or the device under test is being simulated by this Fluke 117 digital multimeter, just as we've done before. And you can see the current, 0.850, so really close to the values that we saw before. That would vary just a little, you know, if I bring it up like that. So they're pretty much the same numbers that we've seen before for that current. So again, the current limiting function is working perfect on this arrangement. When you start the Variac out down in this low range, there's no jumping up, you know, of a current, no spikes in the current, very slight voltage, just a little bit of a glow there, very low current flow, just about 1/3 of an amp right there. So again, this arrangement works very, very well. And there's two things about this arrangement that I like. One of them is that you have complete isolation in the components after the isolation transformer. So your AC line is applied to the transformer, and then even your Variac is isolated in this configuration. That's a nice safety feature. And then, of course, the device you're testing is also isolated, and as well as the bulb. So everything that you're working on or coming in contact with over here, you do have isolation. So again, that's a nice bonus to this. Nothing is before the isolation transformer. All right. And then, as I mentioned before, any metering or indication that might be built into the Variac is not going to indicate any losses in the isolation transformer with this setup. So you can see, again, with the schematic here, because everything is after the isolation transformer, any current that flows in the Variac right here is the current that's flowing through the incandescent lamp and through your device that you're testing, and then, you know, coming back around to the other side of the Variac there for that complete circuit. So this bulb, if we install a low wattage bulb over there and have no load connected and bring the voltage up, we have no indication on that bulb. It would remain off. The bulb is in no way affecting any voltage losses between the isolation transformer and the Variac, as we saw in the other demonstration. So my recommendation in building an isolated dim bulb tester is to use this layout. This works very, very well, and again, it's the one that I use on my bench. If you enjoyed this video, don't forget to give it a thumbs up. And if you're enjoying the videos on this channel, don't forget to subscribe. And also don't forget to tap that bell symbol so you'll be notified when I do post a new video. So until next time, take care, and thanks for watching. Goodbye.